Hello friends, this is Manaki or Civil Pro, and today we will do the tutorial of a building in STAAD.Pro. So let's look at the building first, which I'm going to provide you. You can download this building PDF from the description. This is project number 16, so that you can practice along with me. So the aim of this tutorials is that you practice and learn, and if there is anything you need to ask or you need to suggest, so you can do so in the comment section. Okay, so this is the plan. We have the ground floor plan. Is basically a medical college ground floor plan, and then we have the first floor plan, and then we have the elevation. So I'm going to just show you how to professionally design a building in STAAD.Pro. First of all, before designing this building, you want to make sure you have the design considerations ready with you, so that you know all the things which are necessary. If you design a building, you can find it later also. If some changes are required, you can know what are the considerations, what are the live load, live dead loads, seismic load, wind loads, which you have considered for the design of this particular building. So always it is important to write the design considerations, structural design considerations, which you are considering. So first of all, we'll prepare that, and before that, since we are designing this in STAAD, we may put the coordinates also in the PDF. So I'm using this Foxit PDF. Some people also ask me which PDF reader I'm using. It's easy to comment and write. You can also use in any PDF. This comment feature is there, even in Acrobat. So in STAAD, if you notice, the coordinate system is like this. Okay, so if you go to the STAAD top view, the coordinate system is like this. I have to delete this. Delete. So the coordinate system is like this. So this is x and x, positive x direction, and this is positive z or z direction, whichever you might call it. So if you denote this point as 0, 0, and we can move forward to here. So in this drawing has been made in center to center. So it's very user friendly in the sense that anyone can, beginners can also very easily do this. Okay, so practice, it's very good. Okay, so we can give this partition if we want. Yeah, we'll give this later. Maybe we can just put offset in this and then give the partition like this later, but let's go ahead with the main things. Okay, so this will be 4.975, 0. So since this is x direction, all z will be 0 here. Okay, so this will be next coordinate will be, you have to add, right? So just open the calculator in the background here. So 4.975 plus 4.975, which equals 9.95. So here it will be it happened. Okay, 9.95, 0. So I'll just place this here, and again the next coordinate will be 9.95 plus 2.7, which equals 12.65. So it's 12.65, 0. 12.65, 0. So the next coordinate will be 12.65 plus 4.975. It will be 17.625. 17.625. 17.625, 0. Put it here. Oh, not here, actually it will be here. And then 17.625 plus 4.975 again, plus 4.975, it is 22.6. So it is 22.6 here, 22.6, 0. Okay, so this is done. Now this part is 1.8, so every coordinate will be same except the z coordinate here will be 1.8. So this will simply be 0 comma 1.8, since z is positive in the downward direction, so it will be positive 4.975 comma 0, and then we have 9.95 comma 0 here, and then we have not 0, sorry, so this will be 1.8. Okay, now this coordinate also the same, on we have to add this, so it will be 1.8 plus 4.375, 1.8 plus 4.375, which equals 6.175, which will be the coordinate for z here, 6.175. So it's already written, this 7.975 is the coordinate here, 975 is the coordinate. So these are the coordinates for this ground floor plan, and then we can move forward if we do the structural design considerations. So let's do the structural design considerations here. So we'll edit this. This is the format here, which will be available to you. You can make a better format also. Medical center, you can use. Building type is building type will be G+1. Floor to floor height will be mentioned in the elevation. It is 3 meters. Plinth height is 0.45 meters. foundation depth from soil test report, we'll take this as per soil test report. So foundation depth is 1.5 meter and plinth height is 0.45 meters, so it will be 1.95 meters. SBC is 1. SBC, this will be taken from the soil test report, so we'll take keep this. Building design will be done by STAAD.Pro software. Grade of concrete is M25 and grade of steel is FE500. Initial section considerations here, this will be 400 into 400. The column size, plain beam size 300 into 300 into 450, root beam size 300 into 450. We will take in this particular building. So here we are using STAAD, so we are using by coordinates, so the grids are not required, so we'll just delete this point. And then the dead load considerations, self weight will be automatically calculated by software. Wall load on beams, so 20 kilonewton per meter cube is the unit weight of brick and plaster combined. So actually a unit weight of red brick is 19 and plaster is 20.4, so approximately if you take 20 then it should be coming as right. So here 0.25 is the thickness of the wall, 10 inches approximately 0.254. So and this will be the floor to floor height. So anyway we know the floor to floor height is 3 meters. So the distance which will be remaining is 3 meters minus the beam size. So beam size is 0.4. So if we do 3 minus 0.4 is coming as 2.6. So instead of 3.45, this is the height of the wall. It will be 2.6, and we'll do the calculation here. And 20 into 2.6 into 0.25 and 13 kilonewton per meter will be applied on the walls. So do 13 here. And wall load on the beams, so will be there is no roof truss, so this point is not valid, and there is no roof truss, so these points will be, this point of last point also not valid. So floor finished loads for tiles, marble, whatever will be put in the floor finish will take 0.5 kilonewton per meter square. You can find out in the IS 875 part 1 in table number 1 that for clay tiles is mentioned. Ranges in fact below 0.5 kilonewton per meter, but we are taking on the little bit higher side to be safe. Now live load, you first have to identify the type of the building here. So let's open the code and find out that. So I've opened the code, we have opened the code here, and firstly before going into table number 1 you have to identify the type of the buildings. Which type of the building is it? So you have to go through these buildings here. So type starts with assembly buildings. In assembly buildings we have recreation, or let's see the plan first. So you can see this is the medical service center, and you have OPD, toilet, veranda, but it is actually medical service center, so can be classified as a hospital. So let's look for which building category a hospital comes under. So you have recreation, so definitely not recreation. Motion picture halls, city halls, clubs, I don't think it will be this building. Business building, definitely not business building, definitely not an office building, definitely not an educational building or an industrial building. Institutional building, so you can see it includes hospitals, sanatoria, penal institutions like jails, so it's a institutional building. So here in the building type you have gone for institutional because it's a hospital. Medical service center maybe, but it's classified as a hospital. So now we have to look in the code of institutional buildings here and find out that which live load we need to apply based on the rules. So based on our plan we have OPD, and we have some rooms, toilets, etc. We might even have some, yeah, we have OPD basically. So these are the things which you have. So we have to now look in the code and find out the suitable live load for that. Bedrooms 2, kitchens, laundry, and laboratories. So in OPDs mainly, yeah, if there is OPD, there may be a lab also be constructed. So 3 can be, I think, the minimum thing here. Toilets and cafeterias 2, X-ray rooms, oh yeah, we found the exact thing. Operating rooms, it is 3. Office and OPD rooms, it is 2.5. So this is, in this there is no operating room, but we have OPD. So for OPD it is 2.5, but let's go on the higher side just to be safe. If that medical service center wants to install an X-ray room or operating room, we don't want to be that on the lower side. I think 3 will be a reasonable assumption here. So you can see, I'm just letting you know the mind assumptions of a structural engineer. So how to do this? So that's the things which you need to consider. So we are considering 3 kilonewton per meter square for this building type and for this plan specifications which are mentioned. And then there is no roof truss. Earlier project there was roof truss, so it was mentioned here. So dead load and live load part is completed. Now we go for the wind load. So this is the basic wind load category. Our building lies in Tripura, so basic wind speed there is 55, terrain category 1, and all these factors you can check the code out. I'm not going to go in that much detail here, but I have the pages in here, so you can check the code out. These pages are the pages of the PDF. So if you enter this number in the PDF, you'll get to that particular page. Okay, of 875 part 3 2015. I should mention this because some people are using the lower older version also. This will all be, these page numbers are all in 2015 PDF. Okay, so seismic load here, seismic zone factor is, seismic zone is 0.5 and seismic zone factor is 0.36. Soil type is medium. You can see this you have to find from the soil test report. And response reduction factor is 5 here. We have the response reduction factor which is 5, and importance factor is 1 here. This will come under all other buildings here. Very important buildings, let's see. Important buildings like critical government buildings, signature, lifeline, emergency buildings, hospital buildings. Okay, so importance factor here will be 1.5 because this should be classified as a hospital building. This is an importance building, can be used in terms of emergencies if there is an OPD, definitely. So we have to go with 1.5 here, and the damping ratio is 5%, and since it lies in, you can see damping ratio clause I have given here. Every data is given here. Vertical earthquake effects are to be considered, yes, because the structure is lies in zone 5. End of conversation. Because effect due to vertical earthquakes as per the code 6.3.3 should be considered if you have any one of the following conditions. So you have to satisfy this code, and so you have to consider vertical effects also. So in ETABS, the 2016 version, you couldn't apply the vertical effects in the static load. You could apply in the dynamic load, but here in STAAD we can apply in the static load as well as in the dynamic load. So percentage of the imposed load to be considered will be, our seismic load is above, if it's above 3 then it's 50%, if it's up to 3 then it's 25%. Our live load is exactly 3, so we'll consider 25%. Good, fair enough. Flow diaphragm is needed to be considered for the wind loading. So flow diaphragm will be considered, and the flow diaphragm will be considered rigid. So and flexible diaphragm is for special condition. You can read the clause. Crack section properties will be considered as per 6.4.3.1. These are all clauses of the earthquake load, IS 1893 clause. So this is the main clause which I'm focusing on. So we'll take 70% for a moment of inertia for columns, and 35% will take for beams. And method of structural dynamic you will use both the dynamic and static method in STAAD, and for dynamic method we'll use the response spectrum load. So what is the response spectrum? It is a representation of the maximum responses of a idealized single degree of freedom system of different natural periods but having the same damping under the action of the same earthquake down motion at their basis. The response referred here can be maximum absolute acceleration, maximum relative velocity, maximum relative displacement. So acceleration is absolute, velocity is relative, velocity and displacement both are relative. So if you remember that in physics we used to have this differentiation. So if you differentiate single differentiate displacement, you get velocity, and if you double differentiate displacement, you get the acceleration. So these are the responses which you find in the earthquake. Okay, so this is the responses which can be referred. So basically the natural periods are different, but the damping which is the same. So again, this is the response spectrum. So you're not using ETAPS, so I'll not use this scale factor here. In this thing is not required here. This is exclusively for ETAPS, but scale factor is there for, you know, in the code as well. So I'll keep this portion blank for now. Modal mass and number of modes checked. So number of modes need to be checked, and number of modes should be at least 90% of the total seismic mass. So and another clause which is in table number 6, it is given the first three modes should be considered should constitute 65% of the mass participation factor in each principal direction. So we have to check this out. I've heard from professors that this second one will be changed, so we're not focusing on the second one, we'll just focus on the first clause. Okay, so these are, and after we design, we'll just write down the final design considerations here, you know, and these portions will not be required here. Obviously there is no truss here. So yeah, this is all in all, this is it. Okay, there is no retaining wall here also. So all in all, we want the final results here. We'll write the final results here, whatever we get after the analysis. So let's start the modeling part. So let's go into STAAD.Pro, create new project, and save in the desired location. So we create the file, and first of all we put the coordinates in the Excel sheet, and then we paste it here. So we have the coordinates in the building drawing here. So we can go forward and make an Excel sheet in the folder. So one by one, we are just writing the coordinates here. Y, obviously we are taking y as 0 because y you are considering as the plinth level. So any level below will be negative, and any level above will be positive. So if you look into the diagram here, this is the plinth level here. This will be taken as 0, and this will be minus 0.45. And if you go below the foundation level, it will be minus 1.95. 1.5 plus 0.45, 1.95. So like this, it will work like this. So basically in the Excel, it's easy to copy, that's why we are doing this in Excel. So next coordinate is 17.625. We just write the x coordinate 0.625, and then the next coordinate will be 22.6. so we'll just 22.6. And then we can copy this 0 and then paste it here. Okay, and then these, and select these two and click like this, 6 coordinates. Only the z coordinate will change. So first plot and then the second plot. Okay, in here the y coordinates will be the same. Okay, for all this, and the z coordinate for the next 6 will be 1.8, and you can copy these two to here. You can copy this, and for this one the y coordinate will be 6.175. so we'll just write 6.175, and then copy this 6.175 and paste this here. We need another batch here of these x coordinates, and 0, it will obviously be the same, and 6.175 was the last thing, and this is 7.975. so we'll do here 7.975, copy this and paste it here. Okay, now we select these two and double click. So we have total of 24 coordinates for the plinth level here, and these are the coordinates which we are having. So we'll select this like this and copy, and after copying this, we'll just click here in the node number and Ctrl+V and click on OK. So once this is done, we'll go to view and we'll go to the top view here, and you see your plan also to match this plan. And then we are going to join the beams here to geometry, add beam option, and select the beams here like this. Simply left click and then release the left click, again left click on the next point, left on the first point, left click on the next point, like this you do. So I like to go here in a symmetric way, a similar way. Suppose I do the row first and we do the column next. Okay, done. Now we go to select and select the node cursor, select all the nodes here, go to view and take the 3D view, and we go to geometry and we use the translational repeat option and y direction. So we're going to, this is a plinth level, we are going to go in the foundation level and denote the connection between the foundation and the footing. So we're going to go here minus 1.5 meter, number of steps will be 1, and then click on link steps. Since all we have column to column connection, we can click on link steps here and then click on OK. So this is the foundation level, this is the foundation level, and this is the plinth level. So we have completed the modeling up to this. Now if you want to model this also, so for this also you can do this, but since this is the plinth level, we can ignore this part here, okay, or we can insert this portion as well, because this portion is the same in the ground floor and the first floor, so we can model this also if you want. Okay, let's see how we can do this. So we go to view and we go to front view here, and we can select this like this. Make sure the selection line is thin, so that only this part is selected. Right click and then click on new view, click on OK. Okay, so then we go back to the top view here, and in the top view here you can see this, the top view is mentioned here, view from +y. Okay, so this is the top view. Okay, so in the top view what we can do is we can divide this part here. So this is half, actually 4.975, half portion is part of the veranda and half portion is a toilet. So we can put a line at the center here. So the easiest way to do this, I think you can go to geometry, you can click on add beams. You can see click, do you want to add a node here? Yes. Add midpoint, okay. And here also, do you want to add a node here? Add midpoint, okay. So this is the simplest way to do this. So let's do this like this. Add midpoint, okay, and here add node here, add midpoint, okay. Simply just continue to do this. Okay, done. So we have completed, as you can see, now the beam is divided. This portion we have the staircase, so that's why you're not giving this. But in the plane beam we can provide the beam here actually, but in the roof beam portion, when we provide the roof beam, we cannot give the Yeah, in the roof beam portion also we can give the beam here, because this will be the landing. Okay, landing. So we can provide the landing beam here, but there will be no beam in this portion in the roof level. Okay, so because otherwise it will obstruct the the people who will climb their head will might hit that, so they will not get a clear height for this particular flight. So this beam will not be present in the next level. So you can ignore this at the plinth level also, if you want, or we'll keep this at the plinth level. So if you want to go to the next floor, we'll select all this, okay, except this beam, which we don't want. And after that we can go to the 3D view. Remind you that this is only the plinth level selected here. Below the foundation level is not selected. So you can go to the view and we can go to the isometric view here, and we are going to use translation repeat. We are not going to use the link step because there are secondary connections here. This portion doesn't have column, this portion doesn't have column, so these are secondary members here. So you are not going to use the link steps in this particular option. So we're simply going to geometry, and we're going to use the translation repeat option in the y direction. And the default step spacing, you can just check the structural design considerations which you have already written here. Floor to floor height is 3 meters, so we're going to go with a 3 meter height here, and no link steps, and then click on OK. Now what you're going to do is you can rotate with the help of your cursors in your screen, direction cursors in your screen. So in this we're going to right click again and click on new view. Since this is already selected, we are going to only select this particular portion here, and in here we are going to select with the help of the node cursor. So we're going to go select, and we're going to take the node cursor. So only the primary connections which have column, will select those nodes. So these nodes have the primary connections, these are the staircases, these are columns. So these are the portions, all the nodes selected which are columns, so they will go upwards. So now I can use geometry, and I can use the translation repeat option, y direction, and 3 meters I can use the link steps option, and click on OK. Now let's see the effect in the display hole structure isometric view. So you can see the steps are connected here like this. I can go back to normal cursor by clicking, twice clicking on escape. I will go back to the normal cursor here like this. So you can see this structure. Let's see, this portion will have a slab or not in here. So we'll climb this portion will have slab, only this portion, the staircase portion, will not have slab. So the slab in this particular portion, 1 2 3 4, this particular portion will be there, so there is no problem in that. So we'll go one more floor. So view and front view here, select this, so check in the 3D view, and we're going to go one more floor. So use the translation repeat option, no link steps. Okay, now we're going to use the link step option. So right click and then new view, and then view, and then click on the top view here, select node cursor, select this once again, remember to press Ctrl, otherwise your selections won't stay. So I think I forgot to tell that in the previous time. Okay, those were new. Okay, so Y, and then default 3 link steps, click on okay. View display flow structure, so automatically will get tuned into the 3D view. So this is the ground floor, the first floor. So this floor will actually be the terrace, so we don't need this intermediate beams here, these secondary beams here, we don't need that, so we can delete that. So for that we have to select, go to a better view here. Let's go to the front view here, and take the beam cursor and right click and click on new view and click on OK. So let's look from the top here, and in this we'll first of all use control and to select all these, and delete this. So after deleting them and select these and maybe this and this. So non-collinear, just select and go to beam tools and merge beams. Merge. And merge. Okay, select to select them again. Oh, all entire beam became one. So we have to go with non-collinear items here. I think the best way is to delete them now. Okay, so add beams. We'll just add the beam. So you can now select the beams which are in a line. So when you merge beams, make sure that this one will not be there. Merge beams, make sure that you have the things are not in the same line. I thought. Okay, select this and then go to beam tools and merge beams. Merge, close, select. Okay, this also is messed up because I had done that, but select this and select this and select beam tools and merge beams. Merge and close. So select these two and beam tools and merge beams, merge, close, and remaining portions we will just add the beams again. So one by one we have to do. Select these two and beam tools, merge beams. So if you want to see the beam number, press Shift plus B in your screen, the beam number will appear. So suppose I'm selecting these and this, and then go to beam tools, and then we are going to merge beams. So you can see 224 and 225, these beams are merged, so that you can have an idea. You just go back to Shift plus B to remove this and display whole structure once again. Okay, so here you can see we remove the unnecessary part. So the headroom portion we need to do. So we go to the front view. So we're going to do the Mumty portion. Right click and click on new view. Okay, top view. Select the Mumty portion in here. Okay, this is the Mumty portion, and we'll use the geometry translational repeat option, and you can see the Mumty height in the elevation, or this is also called the headroom or the staircase room. So 2.4 meters is the height here. So Y and 2.4 meters is the height of this Mumty, and then we'll click on we'll not click on link steps now because there is a secondary beam here. Oh yeah, no, there is no secondary beam. All things which have columns, so we can just click on link steps here. 2.4 meters link steps, click on OK. Y direction, view whole structure, display whole structure. So this is done here like this, and now we can go to the supports option here, and in fact let's go and click on the property, because it's good to go in this panel so that you don't forget anything. Because I figure the geometry we've done with geometry, then we'll go to properties, then materials and specifications, then supports, and then we'll finish, call it a day for the modeling part, and then we'll go to loading part. Okay, yeah. Now properties. So in the structural design considerations, we had already considered the column size and beam sizes which we would consider. So 300, 400, 400 for the columns, and 300 into 450 for the roof beams, and as well as the plain beams. So let's go. So we'll go rectangle here, and we'll go 400 into 400, which is the property for the columns. Close this, and for the beams we'll go here 300 into 450. 300 into 450 will be for our beams here. close that. And now you can either assign the slabs, or you can put the load of the slabs. Okay, so we're going to assign, we're going to put the load of the slab in this case. Okay, so there are two methods to do this. Either you can assign the slab. If you assign the slab, you don't need to consider the self weight of the slab. If you don't assign the slab, you have to consider the self weight of the slab. Okay, so we'll consider the self weight of the slab. So we're not going to assign in thickness, otherwise you can assign the thickness and put the slab here. Okay, so yeah, let's go. Select the column property, go to click on select parallel to, okay, this is beams parallel to Y. Assign to selected beams, assign and yes. Select the beam property and select parallel to X, parallel to Z, and then assign to selected beams here. So this property has been selected. Now materials, by default all materials are concrete, and we'll go to specifications. Now in the specifications we need to put a criteria which is mentioned in the Seismic code actually. So this criteria, two things actually we have to do. Firstly, the criteria of the crack sections as per the clause 6.4.3.1 IS 1893 2016. So column 70% and inertia for beams 35% we have to take. So just click on beams here and property reduction factors. Moment of inertia you find here. Let's define for the columns first 0.7 and also 0.7. Click on add. And for the beams, property reduction factors 0.35 and 0.35. So let's do the assigning part. Select this, and this is for the columns, we know parallel to Y. Assign and yes. You can see this has been assigned here in the edit list. If you want to see and check the edit list, you can just press Shift+B once again. Just check 39. You can see this is the thing here. So going towards the next property, select the property for the beams here, and we use the select option parallel to X and parallel to Z, and then we assign and yes. So this property has also been assigned. You can see the edit list. So you can see 1, 2, 3, 4. So you can see 1 to 38 all are the beams. So you can justify this from this. So we press click and press Shift+B again to remove all this, to just not go into that hodgepodge kind of a thing. So then we click on the notes. So now we are fulfilling a criteria of, again I can say the Seismic code as well as the wind load code. This is the criteria of the diaphragms. So you can see we are considering the rigid diaphragm as per the Seismic code. So diaphragms are the portions mainly loosely translated. It can be when we have a slab, wherever we have slab, we'll have the diaphragm which will transfer the loads to the beams and then to the columns. Okay. So this was an old process, and floor diaphragm we have this new process. We'll create 3 diaphragms here, and we'll have the height here which will be given here. So height for the first diaphragm, in the floor to floor height is 3 meters, will be 3, and it will be calculated, and we'll just click on this portion, define floor range. Okay, so we'll select the nodes, okay, and add. So again we'll select the second diaphragm. This diaphragm was this, and second diaphragm, and this time the height will be 6, and remember to select this and do select nodes option and click on add, and then use the select node beam cursor to check the height here. Height is simply the Y coordinate, so Y coordinate is 8.4. so next diaphragm is actually 8.4, height will be 8.4. click on define floor range and select nodes, add. So first diaphragm, go to view, go to front view, just select this with the help of node cursor. First diaphragm at 3, done. Second diaphragm at 6, done. Third diaphragm at 8.4, done. So the diaphragms have been defined. Now we are over with the specifications part. Now we are going towards the supports part. Okay, so for the support part, we'll just create a support here and we'll click on add. So we're considering the fixed support, which denotes the connection between the column and the footing. So it's better to go in the front view. You can have a shortcut for the front view, which is Shift+1. So select this and you can see the effects in the 3D view as well. All the nodes are selected. So assign and yes. So you can see the nodes are selected here like this. So we can let's also assign the just you can see the effects in Ctrl+4. This is the rendering view, and again if you press Ctrl+3, you will find this view in which you will see the frame structure in the STAAD.Pro itself. So you can observe the frame. So it's complete up to the mountain level. You can see we have not assigned the slabs here, because we'll put the load of the slabs in here. So press Ctrl+0 to go back to the normal view. So now the modeling of the structure is completed. So before you go into the loading part, so I'll share another PDF. This procedure is purely the procedure for doing the things in STAAD. So we'll have to calculate the time period. So the time period will be for the time period to be calculated, firstly we have to calculate the acceleration. This is calculated automatically in ETABS, so you don't need that, but in STAAD we need to calculate this. So yeah, anyway, so we'll follow the clause 6.4.2 for calculating the acceleration, which will help us to calculate the time period. So acceleration here will be calculated first, and for the acceleration only the important factors are the dimensions here. So you can see this is the formula for calculating the time period here. So first of all we have to this is the clause number, you can see 7.6.2 of the IS 1890 2016. So you check out this clause, and part number C, TA. So h is the height of the building. So height of the building is 3 meters for the one floor, so 2 floors it is 6 meters, and if you consider the plinth height as well, it will be 6.4, but it will take 6 meters building height. And then the base dimension here, you can see this is 2.6 into 7.95. So x, it is 22.6 meters in x direction. So along x it is 22.6 meters, and along y it is 7.975. So 7.975, and this is the 7.975, and height of the building is 6 meter. And now using the formula we just put in here, the height of the building is fixed here, it will be 6. For this also it will be 6, only this will be changed, 22.6 here, and here it will be 7.975. So calculating this, let's use Excel, 0.09 into 6, divided by square root of 22.6. So it's 0.11, and only this will do change the square root. Instead of 22.6 it will be 7.975. So just do this 0.19. Okay, so now with the time period of both this, Seismic mass will define when you open the code, but let's just move here and calculate the time period. So yeah, I think we can copy this, it will be easier. Sorry, acceleration, sorry. So we can calculate time period here, Just copy this changed thing, and for calculating the acceleration now, pasting it here. So you can see 0.11 and 0.19. So for soft soil, see, if we are using response factor, so for soft soil, for 0.1 to 0.55, SA by G is 2.5. Z, we know Z is the zone factor, seismic zone factor, which is in table number, this table number 0.36 for zone number 5, since our building lies in Tripura, seismic zone 5. And R is the response direction factor. Response direction factor can be taken as 5, importance factor is taken as 1.5 in our case. So we can calculate this easily. So SA by G, H and X, both H and X, SA by G is same, 2.5, so it will be calculated as the same. Okay, so yeah, only one we need to calculate, H, X, Z and X. If you do Z and X will be the same, so it can be different for other cases, but in this case acceleration in the Z and the X direction is the same. So it will be Z by 2 will be 0.18, SA by G is 2.5, we take from here. R by I will be 5 by 1.5, importance factor is 1.5 here. So we'll just calculate the value here, is equals to 0.18 into 2.5 divided by 5 by 1.5. So it comes as 0.135. So we write here 0.135, and for the vertical direction it will be as per this clause 6.4.6. so it will be 2/3 of this value actually. So if you do 2/3 into this, then we will get the answer. So is equals to 2 by 3 multiplication of this value here will be 0.09, I think, yeah, 0.09. So 0.09 is the seismic in the vertical direction here. And we will have the eccentricity will not consider now, and we'll have the earthquake load combinations in all three directions. So for that we'll add the earthquake loads manually, so the load combinations manually we'll add. Okay, so let's do. So we'll open the STAAD model here. So first of all we'll go to loading. So now we'll do the loading part. So firstly we'll define the reference load here. Reference load definition will be done, and loose seismic mass or the structure mass, whatever it is the name, seismic mass, will define this. And then this will be type, load type will be mass. Okay, mass here. So we put search for mass and put this at. So this is seismic mass of the structure. This will be used for creation of the wind load as well, wind load definitions as well as seismic load definition. So seismic load definitions here, and we are going with 1893 2016. Generate the value here, zone 5, special moment resisting frame, and importance factor is an important building, structure resting on medium soil, and damping ratio 5%, period in X and Z we just calculated. So we'll just keep the values here, insert the values here from this Word file which we have, which I'll give you in PDF, I think, or what. So here we have the 0.11 and 0.19. So we have the values here, 0.11, and we have this value as 0.19. So we click this generate and click on add. We close this. Wind definitions also we want to do here. Wind definitions, wind 1, click on add, close. Now this wind 1, this will be custom, because in this particular version of STAAD which I am using, the Indian codes are not there. If you are using European codes, SC codes, you can calculate, but we'll just calculate using an Excel sheet, which also you'll find attached. So no problems, everything I'm giving you. Now this one, this one, this one. So here the height of the building is less than 10 meters. We can use simply this particular value 10 and 1.475. So the total height is less than 10 meters. We'll use this 10 meter 1.459 we'll use. So we'll use this at height 10 meter. Intensity in kilonewton per meter square is 1.459. Okay. So click on add and close this. So wind is defined. Seismic mass seismic definitions is defined. Seismic mass will complete later after completing the dead load, live load. Okay. So we'll add the loads here. Primary load. We'll use the first of all we'll have the seismic load. So SLX will be added first, and then we'll use the SLY will be added second, and then we'll use the seismic load Z direction. So Y is the vertical load in this case, and then we'll add the dead load. So these are the static loads which have been added. Dead load we'll add, and then we'll also add the live load. Then we'll add the response spectrum loads here, and then seismic loads. So it will be RSX, RSY, RSZ. Then we'll add the wind loads here. So we'll add the wind load in the four directions which you're having. We'll apply the wind load here: W1, W2, W3 and W4. Okay, close this. Seismic load we'll add. So we'll click on seismic loads, X direction, factor of 1, click on add and close. Seismic load in Y direction, click on add. Factor of seismic loads, factor of 1, Y direction, click on add. Seismic load in Z direction, click on add. Seismic loads Z direction, factor of 1, click on add. Dead load, click on add. Firstly, we'll add the self weight. Self weight of the structure has been included, and then the member load. So in the member load, let's open the structural design considerations here. This will not be required for now, and this will also not be required for now. So we'll open the structural design considerations here. So here in this part where you have the loading parts, so in the dead load we calculated the wall load and beams, and this is for actually this is for ground floor and first floor. So for the terrace we hadn't calculated. For the terrace we also calculate this wall load and beam. Simply we will copy this. So terrace portion of this we can write as terrace. Okay. In the terrace you can see the height of this parapet wall is 1 meter. So this will be coming as, instead of 2.6 we'll have 1 meter here, and we'll calculate in Excel 20 into 0.25. You don't need Excel for this. 20 into 0.25 is 5 kN per meter. We'll apply in the parapet wall region. Terrace for parapet wall. Okay, and same thing we'll do for the portion where we'll have the mumty. Okay, so this will be for mumty. For mumty height will be this height is 2.4, and if you deduct let's say beam size of 450, then it will be 1.95. So 1.95 will be the height for the mumty. so into 1.95. This will be for mum. Mumty. I like the term headroom better. Okay, Mumty headroom, staircase room, whatever you. Oh, so spelling is wrong. Mumty. This one is not in the dictionary. So in Google it is there. Mumty. Okay, let's not get into that. Okay, I will check later. I can also check and let me know. So Mumty or headroom. So this is 5. Now Mumty or headroom portion will apply this. So okay, so let's use the dead load. 3 dead loads we will calculate for the wall, 13, 5 and yeah, we may ahead and calculate that. So it will be 20 into 1.95 into 0.25. It will be 9.75. So okay, so let's go and calculate, provide this. So firstly we'll go with minus 13, click on add, and then minus 5, click on add, and then don't need this now, and then we 9.75, next load minus 9.75, click on add, and then these are the wall loads which are done. Now for the floor load, first of all let me add the load of the slab, since you have not modeled the slab. So slab load, I'll just do this. Consider slab thickness of 150 mm. Slab load, since we are not modeling this, will be calculated as 25 kilonewton per meter cube, which is the unit weight of concrete, into 0.15 meter, and the answer will come as 25 into 0.15 come as 3.75 kilonewton per meter square. 3.75 kilonewton per meter square. This will be the slab self weight. So let's consider this 3.75. Floor load minus 3.75. so slab will be coming in that, just define the y range. In this is 0, this is 3, this is 6. First of all, so we'll go here, it will start from 2.9 minimum range, and maximum range it will come in 6, and then 8.4, I guess, yeah, 8.4. so 8.6 to 8.5 we'll put x range, global y, done. And again the parameters will be the same. We'll add the floor finish load minus 0.5. This will be the floor finish load here, which we'll add. Okay, so this, then we'll close this, and then we'll assign the loads here. Self weight we'll just do assign to view. Now this 13 kilonewton per meter square will go front view, shift +1, and select this floor, and control and select this floor. So you can see in the 3D view which portions are selected. Here we'll apply assign to selected beams, assign yes. Now for 5 and 9.7 we have to move to the terrace. So let's move control +1 to for the front view, select this and right click and new view. Okay, top view. Now 5 will be applied here, 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 and here. assign to selected beams, assign, and yes, 9.75 will be assigned here. Okay, done. Now for the live load portion, we can simply copy this and put the live load here. This is okay. First of all, display whole structure. I can see live load, red portion, blue portion. You can see the live load which has been assigned. This was the load for the slab, and this was the floor finish load. Okay, so the next live load will use the stat command file. So go to utilities and go to command file. The structure has been modified, so we'll go to more command file and we'll zoom in and move down here, and in here we'll copy one of the floor loads here, copy, right, click on enter, paste it, and instead of 3.75 we'll look on the structural design considerations, and our structural design consideration live load was 3, so let me enter here -3 since it's acting from top to bottom here, vertical direction, so -3, Ctrl+S, and we'll see the effects here. So let's see our changes was made or not. Changes were made or not. So let's see, this live load has been assigned here. So live load and dead load part has been completed. So since our live load and dead load part has been completed, now we can define the seismic mass. Okay, seismic mass already has been defined. We can complete the seismic mass or the reference mass. So we'll go to the utilities, we can go to the command file, and here we will find out where the seismic mass definition or the reference load definition has gone. So correct float diaphragm. So the reference mass should be before the you can see different and different, it should be before the diaphragm. So we'll move this before the diaphragm here, Ctrl+X, and just before the diaphragm we'll enter this reference mass. So first of all we'll observe whether there is any problem due to this on the model or not. So we'll check in the specifications where the diaphragm is assigned. It is assigned, you can see the values here, it is assigned, and you'll check in the loading where in the definitions here the seismic reference load definition is there. So we'll go back to the command file, zoom in with the press Ctrl and just scroll in your mouse, you'll zoom in, and in the title seismic mass we have to enter stuff here. So dead load, entire dead load, just copy, so I have completed the entire dead load, and for the live load also let me just copy, live load, will just press OK. So now member load, this is fine, GY -13, we have to remove the sign here, and we have to provide this same load in all the 3 directions. And okay, so one will be X, let me turn the caps lock, X, Y and Z. Fine, now this load in the 3 directions. So one by one we are going, you also follow, I recommend you follow the same procedure, otherwise you will be confused. G, X, GY and GZ. Same thing will be done for this. Very simple. Now GX, GY and GZ. Now for the floor loads, same thing will be done. Copy this, Ctrl+C, Ctrl+V, Ctrl+V. X, Y and Z, and for this 0.5, copy this, X, Y and Z, and then comes the flow load for the live load. Now flow load for the live load needs to be a percentage. So what's the percentage? It's given in table number 10. So we are taking, you can see in the structural design considerations itself that in table number 10, where is it? We are taking actually 25%. Okay, so we're taking 25%. Let me just find that real quickly. Oh yeah, this, we're taking seismic mass 25%. Percentage imposed load to be considered in seismic mass is 25%. So we're taking 25%. So 3 into 0.25 is 0.75. So we're taking 0.75 here. So 0.75. Now this will be applied in 3 directions. Control plus C, Control plus V, Control plus V, Control plus S to save this. Now the reference mass definition which is complete, it will be used in the seismic mass calculation as well as the wind load calculation. So let's close this for now. And in the loading patterns, in the definition part, let's see the effects of our alterations. Here you can see in the seismic mass, the seismic mass source has been created. So if we define the reference mass here, we don't have to define the reference mass in seismic definitions. By the way, if you define it also, then it will not be any problem. It will take the one in the seismic definition. Okay, by the way, don't not need to define that twice. So let's go. Static loads has been covered, dead load and live load has been covered. Now coming forward to the response spectrum loads. So we'll add the response spectrum load here. Click on add, and here you have the response spectrum. Okay, just go for the code here. First of all, let me select the code and go for any of one of the methods. Go start with SRS, SRSS. If this is not sufficient, chat will give you a message and you can change the method later also. So no problem in that. Our soil is medium soil, and now the acceleration which you have calculated with the help of the time period, you just insert it here. So since this is the X direction, we'll insert the acceleration in the X direction. So it is 0.135 which will be done. So 0.135, and it will be, click on add and it will be added here. RSY, so Y is the vertical direction, so we'll add the response spectrum, add the seismic code which will be 192,016 and medium soil, and Y, and this is 0.09 for the vertical direction. So 0.09 for the vertical direction, and click on add. Close this. Similarly for the Z direction, add response spectrum, selection of the code, medium soil and Z, and this will be 0.135, and click on add and close. Okay, so this has been defined, seismic load. And now, so response spectrum has been defined here. After the definition of the response spectrum, now comes the wind load. So wind load will apply in all the 4 directions. So we'll first of all go and select the node cursor here. We'll add the wind load here. This is not the perfect way to put the wind load, but this is usually the result comes on a bit higher side, so we will be safe. The design will be safe anyways. Windward phase 1, and Y range will start from 0. We don't want to apply to the staircase room. 0 to will be 6. So 0 to 6 will be the Y range. X range 0 to 0 to 0, so it will be 0 to, let's go 0.1, so everything is 0 here. Z range starts from 0 and with 7.95, so 0 to 8, let's put. Click on add. Get added. Let's close this and let's see the effect. So it is going correctly. So this is the first W1 in X direction we got, and then we'll apply in Z direction. This direction we'll do. So this will be in Z, and this was positive X, and this will be negative Z. Z will do at space, and I think factor -1 will be the proper analogy. 0 to 6, X range starts from 0 and ends with 22.6. 22.7, let's put. Okay, and Z range starts from 7.975, so let's put minimum 7.9 and maximum is the same, 2.8. Okay, add. Let's see if this is going in the correct direction. Perfect. So now in this phase, so we'll add here window load, factor of 1, minimum, maximum, Y range. So let's look into the X range here. You can do everything. You don't need to rotate the model. You can see from here this X range is 22.6 and this is also 22.6, so I can go do at 22 to 33, 22 23. This will be sufficient, I guess. And the Z range is 7.975 and 0, so I can do 0 to 8, 0 to 8. And the direction here, it will be, I think, a negative X direction, so X and then -1. Let's add this and close. Let's see this. So it's also coming perfect. Now W4, click on add, window load, minimum 0, maximum 6, X range. It's 0 in here and it is 22.6 in here, so 0 to 23, let's put. And Z range, it is 0 in here, Z, and it is also a 0 in here, so let's put 0 to 1. And the direction, which is very important, I think this is positive Z direction, so Z direction +1. Click on add, click on close. Let's see the effect. Perfectly done. Now what we'll do analysis and design. Analysis commands, do all, click on add, click on close, and let's see if we have any errors here. So for seeing that, we'll run the analysis, save the model, and the analysis will run. We have 2 errors. Let's fix that. So it's telling there is no support input, so we have to define the reference node after the supports. So that's the one error message, and another message, okay, support. So I think this is the thing here. So I'll go to command file. So the reference mask, reference load definition, I think support definition should be before the this thing, Ctrl+X, and before the reference mask, member properties, concrete, let's put the support here, Ctrl+S, close this, and then let's do the analysis once again. This time I think there will be no error, but there will be some warnings, so we'll fix those warnings one by one. So yeah, one warning I already know, but I just still to show you the warning here. Go to output file. Now how to remove this one by one. Will do 0 warnings. So first of all, let's see the warning. This UVC has tension and compression. So how to fix this? Let's fix that first. Okay, then we'll see about remaining warnings. Okay, so we'll go to the utilities, we'll go to the command file, and we'll open the loading, especially the static seismic loading. So it is SLX, SLY, SLZ. So after this we'll just put perform analysis there, this one, and then there will be change. So this command will just put in seismic Y and seismic Z. So it will get out of this particular command, so it will not have that particular warning. Run analysis. 4 warnings were there, right? 3 warnings, so that warning has been removed. View output file. So UVC compression, that was the warning here. So now you can see that warning is gone. Another warning, which is some modes are very closely spaced. I told you that STAAD will automatically give us the mathematical method for the response spectrum method. So since the modes are closely spaced, so they are suggesting that we should use the CSM method of modal combination. Very good, no problem in that. So we'll go to loading here and see the response spectrum one by one, or even if you change one, then also there is a trick. So we'll just do CQC. Okay, change, yes, close, RSX, edit, CQC, change, close, RSZ, edit, CQC, change, close, and then analysis and design. Run analysis. Zero warnings. So we have achieved 0 warnings. Let's check the notes also. Okay, because this is very important. This is very first mass model will be formed in the seismic response time history loading. So we have used the reference mass, so mass model will be formed. So the seismic mass will be used to calculate the seismic loading. So since our seismic loading is base shear into acceleration, so for and seismic weight, base shear into the seismic weight, VB into W. So W is the seismic mass. So this sorry, I'm just doing that. Base shear is equals to, okay.
Incoming voice call from CATV.
So the next step is equivalent static analysis should be preferably performed for regular buildings. So now this building is a regular building, and okay, just see, regular building, time period less than 0.4 seconds, and height less than 15 meters in seismic zone 2. So for all buildings in seismic zone 3, 4 and 5, our response spectrum or the dynamic analysis should be performed. So we already performed the dynamic analysis. We have already used the static method as an addition. So there is this, we have satisfied this node criteria, and about one-way two-way load. So now basically we have applied the load directly of the slab directly on the structure as a flow load. So STAAD suggests that is best to apply the slabs and then you apply the loads separately. If it's a one-way slab, you just select the property of that particular load So that's better in the technical point of view. So that's the suggestion of the STAAD. So we've not done that in this part, but it doesn't make like that much of a difference here. So masses will form under the seismic load 6 will form. So RSX, definitely the mass matrix will be formed for the dynamic analysis. So that is true. So these are the statements, just the explanation of the statements. So the analysis is done. So and then the remaining is the studying of the analysis and the results. So and also presentation of the final design results. Okay, so that portion is remaining, and also an important part in terms of the analysis is also remaining, which is the load combination part. So I prepared a custom file which I had also shared earlier also, and that custom file was the load combinations for the STAAD. I think it was the this one, service load combination. Yes, this was the load combination for the STAAD, including the dead load. So Ctrl+C here, and then we'll just go to utilities and we'll go to the command file, and here after this before the perform analysis we'll just put the load combinations here, and then Ctrl+S and close, and then we'll perform the analysis once again. Okay, done. Now let's check the design, because if you want the design in detail we have to check the RCDC, but for checking the design roughly, let's design in STAAD only. First of all, we select concrete IS 456, select parameters, which is the minimal parameters which are required. So only the FC, and I want the FC, compressive strength of concrete, and FY main and FY secondary. These things I want here, and define parameters. FC, compressive strength of concrete, will do M25 concrete, and FE 500 steel. Let's go. FE 500 steels. Commands, design beam and design column. Takeoff or the quantity estimation, we don't need that right now. So this will be assigned to view. This will be assigned to view. This will be assigned to view. And design beam, we'll select all the beams here. Select beams parallel to X, beams parallel to Z. Select beams parallel to Y. Okay, done. Done. So once this is done, and then we check the design here. You can see the concrete design. So you can get the AST and then calculate the reinforcement required. Suppose for this particular column, let's see what is the maximum AST here. 28162944 is the AST. So STAAD tends to a little bit just give this quantity of steel a little bit more. So like 2944 is the AST here. So if we just calculate the number of reinforcement in 2944, so we can calculate that. So you can calculate, I have a sheet here, bar radius. So AST required is actually 2944, which is showing. So number of reinforcement here. So if we take 25 mm bars, then it will be is equals to 2944 divided by 490. So it will have 6 bars of 25 mm. This 400 columns, we can provide 6 bars of 25 mm. That should be sufficient. If we go for 20 mm bars, is equals to this divided by 20, then it will be 10 bars. So 400, I think we'll be able to accommodate 1 2 3 4 5 6 7 8 number of bars. So what if we provide like 0 4 into 4 bars of 25 mm, and then 4 bars of 16 mm. So the AST will be 27, then it will not be sufficient. So 4 bars of 25 and 4 bars of 20, then it will be a little bit more on the higher side. So technically 6 bars of 20 mm will be optimal value here. So we'll provide 620 T for the column. So 6 bars of 20 T will be provided in the column of size 400 into 400. Similarly, you can check the beam results also, and with just double click here, and you can check the beam results also. So AST is given 3316 and 3316 and 4975 in the bottom. So in the bottom it is more. So for the bottom 4 bars of 10 mm it is provided, right? So 4 bars of 10 mm and 10 bars of 10 mm. Okay, so from that we find the AST and we calculate the number of steel required. So suppose let's go for the bottom bar, 4 bars of 10 mm, right? So, or let's go for the top one, it's more coming more. So 10 bars of 10 mm. So 10 bars of 10 mm, not this one, this sheet is not required, save this. Okay, 10 bars of 10 mm. So the required AST is, so I'll just write here, otherwise you might, required AST is equals to 10 bars of 10 mm, and provided AST is let's go, if you provide 3 bars of 16 mm, then it will be 3 into 200, it will be 600. So let's go 2 bars of this plus 1 bar of 16. So we have to provide 220T plus 116T. So we'll provide this, both at the top and bottom. So 220T and 116T, both at the top and bottom we have to provide. So STAAD little bit tends, if you go by the response spectrum, tends to give a little bit reinforcement on the higher side, as you can see, but it is safe. It will be, the building will be on the safer side compared, and if you design in ETABS, the designs results are a little bit more economical. So let me know your comments, but this is the entire procedure of designing the building in STAAD. Obviously you can check my videos on RCDC, where you can import the buildings in RCDC and get a perfect sheet detailing and whatnot. But this is the basic point of view, and make sure to practice, and after you complete the practice, come to the comments and let me know that you have completed, and if you have any sort of doubts or queries, ask in the comment section. Thanks for watching, keep supporting, drop a like. Thank you, bye bye.